Welcome back. In our last video, we learned how to create I guess we learned how to create it 2 videos ago, but we learned how to calculate, interpret, and answer several different questions about a one-sample t-interval. And I thought that for this video, which will be the last before your first quiz in Unit 7, that we would do another example. This one's a little different. Let's see how. A random sample of 10 men were asked to test an exercise device from an infomercial 3 times a week for 20 minutes. Their resting pulse rates, which are measured in beats per minute, were measured before and after 6 weeks. So, here we have our data set. We've got our 10 gentlemen here. We have their resting pulse rates before the 6-week exercise period, and then their resting pulse rates after. Okay? And let's say we wish to create a 95% confidence interval for the difference in resting pulse rates, specifically the difference after the 6 weeks minus before. How could we do that? Well, there appear to be 2 samples here. Generally, one of the first things you want to look at in terms of when you want to do inference, whether that's for confidence intervals or hypothesis tests, is how many samples do you have? And it appears as if there are 2 samples here. But we learned something when we talked about doing inference for 2 proportions, right? For the difference in sample or the difference in population proportions. One of the things we had to check was to make sure that the 2 samples were independent of each other, right? Because the standard deviation, or the standard error, both really, of the sampling distribution assumes that those variables are independent. If they're not, you can't use that formula and you're up a creek. So an interesting question here: are the 2 samples of data independent of each other? Again, one sample is the resting pulse rates before, and the other is the resting pulse rates after. They do not appear to be independent, do they? The primary reason why? They're on the same people, right? If someone's pulse rate, resting pulse rate before that 6-week period is relatively high, then you might expect the same person to be relatively high after as well. Same for someone with relatively low resting pulse rate. You might expect that it stays low. Someone in the middle stays in the middle. In order for this to be 2 independent samples, these should be, I don't know exactly how it would be done. I'm sure there are ways, but certainly, if we're taking the 2 samples from the same people, the samples cannot be independent of each other. So despite the fact that we have 2 samples here, since they're not independent, we can't do 2-sample inference on them. So what can we do? Do we just throw our hands up and say we can't do anything here? We can't analyze this data at all? Well, when we have 2 data sets that are not independent of each other, we might consider them as matched pairs data. Restating this a little bit, there appear to be 2 samples here, but they are not independent of each other. So we can't do 2-sample inference. In order to do that, we need to have 2 independent samples. So we're calling this matched pairs data. This is one example of it. In general, matched pairs data records 2 values of the same quantitative variable for each individual or for each pair of similar individuals. So there's a few things about this definition of matched pairs data that I want to highlight. One, it only works for quantitative variables. So when we were talking about the difference of 2 proportions, you can't have matched pairs for proportions because that's categorical data. Matched pairs only exists for quantitative variables where you're talking about means of samples. And also, Matched pairs does not have to be two samples from the same individuals like we see here. I would say often that's the case, but you might have something like maybe if we're looking at hours of sleep per night and our sample has married couples, you would imagine if they sleep in the same bed, it might be that they are not independent of each other. Either they both get a lot of sleep or maybe they both don't get a lot of sleep. So you can have matched pairs data for similar individuals. It doesn't have to be like a before and after. But if you do have data that has this before and after way about it, that is a dead giveaway that you've got matched pairs data. Okay. So what is it we're going to do about this? We know we can't do two sample inference, but we've got two samples here. The great thing about matched pairs data is we don't have two samples here. We have one. How are we going to take our two samples and make them one? We want the difference in the pulse rates, after minus before. So how about for each individual in our data set, we'll take the after pulse rate and subtract the before pulse rate. So we're just calculating differences here. Okay, so we've got a whole new column here, difference, and we can calculate after minus before. So this is going to be 73 minus 73. That's going to be 0. This is 79 minus 83. That's going to be negative 4. And I'll just continue on down the line here. We've taken the rest of our differences here. So we've got our differences all the way down for each of these gentlemen. And here is your reminder. If you have matched pairs data, that's when you have two samples that are not independent of each other for quantitative data, take the difference in the two data sets to create a single data set of the pairwise differences. And does it matter which is which, after minus before or before minus after? Sometimes the problem, if you read it carefully, will direct you which difference to take. In other situations, maybe the difference doesn't really matter. It all depends on what the question's asking, so make sure you read it carefully. But here, since we wanted after minus before, that tells us how to take our differences. And notice, now we have a single data set. So we were never allowed to do two sample inference anyway, because our groups weren't independent. So we solved that by turning our two data sets into one. Now we can do one sample inference. And since we want a confidence interval, this is going to be a one sample t interval for a population mean. We just did that. Now we've got another data set to do it with. It might seem like we're doing some voodoo turning these two data sets into one, but really this is the only way that we can do a confidence interval for this data set, is to take differences and do it on what we've got left. So this is an important point in the video for you. If you feel comfortable, based on the example we've done already in prior videos, you might want to go ahead and go through all the steps for how to calculate this confidence interval for this data set of differences. Remember, first you got to check conditions. Check your conditions first. Then state what you're doing, and then you can calculate it, and then make your conclusion, interpret your confidence interval. You can do that on your own, or if you'd like, you can just continue on and do it with me step by step, if you'd like. Okay? I'll leave the option open for you to work on your own though. I'm going to start by checking some conditions. So if you want to do this on your own, pause now, and we'll see how it goes. All right, so let's check our conditions, and right off the bat, I'll tell you that this is considered a matched pairs t-interval for a population mean difference. I might have said a few minutes ago that this was a one sample confidence interval. Yes, we're doing the confidence interval based on this single data set, but we need to reflect the fact that we have matched pairs data here. We started with two related data sets, so this is called a matched pairs t-interval. for a population mean difference. So this is distinct from a one sample t interval only in the fact that we started with matched pairs. Everything we do from here on out is going to be exactly the same as when we did it for one sample. The only difference is going to be when we interpret our interval. It's not going to be for a single data set. It's going to reflect back to a difference between these two. So conditions first. We need to check the conditions for this data set here. Same conditions. Start with randomization. Do we have a random sample here? It says a random sample of 10 men from our problem. Our second condition, remember randomness, randomization, and this one always go together to prove that each individual is independent of all others in terms of the variable being looked at here. So we need our sample to be random, and we need to be sampling less than 10% of the population. So is 10 men less than 10% of the population? Well, we have to know what the population is. I would suggest that it's all men capable of testing this exercise device. Is 10 men less than 10% of all men who could test the device? I think that's a reasonable assumption. So again, remember, these two conditions, they're not saying that these two data sets are independent. It's saying that the difference in Allen's after minus before pulse rates is independent of Brendan's, is independent of Carlos's. It's independence between these numbers. Okay? If it's a random sample and the 10% condition is met, each individual's difference in resting pulse rates is independent. Last condition, we need to check the large sample / nearly normal condition. Remember, that states that if your sample size is at least 30, you're in good shape. Oops. We don't have that, right? Remember, we're only checking the condition for the differences. So we can't put these data sets together and say we have 20, even though that still wouldn't be enough. Our sample size here is 10. So n equals 10, which is less than 30. So we need to check and make sure that this sample is approximately normal in shape. Unimodal, roughly symmetric, free of extreme outliers. How are we going to do that? Calculator. We need to make our histogram. So you might want to grab your calculator if you haven't already. I've got mine right here. And I've already typed in the data set of differences. Remember, with matched pairs, once you calculate these differences, that is what you're checking the condition for. We are not typing in the original values. We're only interested in these. So we need to take this list that's in L1, put it in there if you haven't already, and remember, for negative numbers, you have to click the negative key. If you press minus, it don't like that. So once you've got all your numbers in there, second, stat plot. We want to turn that plot on. We want a histogram. Our list is L1, frequency is 1. We're going to zoom 9 for zoom stat. And this is what our data set looks like. Now, again, is this approximately normal? Is it unimodal, roughly symmetric, and relatively free of extreme outliers? I would say, based on that, yes. Unimodal, again, remember, when we are looking at the shape of a distribution, we're not interested in the individual bars. It's the general trend of what we see. It starts out low to the left, goes up in the middle, and goes down again on the right. That's what we would expect to see for a normal curve. Is it roughly symmetric? Yes, I think so. There's nothing really skewed one way or the other there. I think it's fine. Is it free of outliers? There don't seem to be any data values that are extremely far away from the rest. I think that this is good enough. Okay. What I might want to do just to make sure, go to Window, and change that X scale to something that makes a little more sense. Right now it's going by 2.25s, so I might change that to 2s. Graph it, and it looks like this instead. I see that this bar here is a little high, so I might change the Y max to something a little bigger, like 5. Okay, so this is what the histogram looks like with slightly different bin widths. I think that's still fine. You've still got unimodal. You've still got roughly symmetric, right? You've still got some values on the left, some values on the right. And I wouldn't consider that bar on the left to be an outlier. It's still relatively close to the rest. I think it's just a quirk of exactly where the data values fall that we see a break there between the leftmost bar and the middle one. So I think this is evidence that we've got what we need. So I'm just going to make a quick sketch of this and show that it meets all the conditions we need to meet the nearly normal condition. I have my sketch here, and I ran out of room, so I wrote what it says here. The data set of the differences is unimodal, roughly symmetric, and free of outliers. So, since all the conditions are met, including these two, we will use a T-model with 9 degrees of freedom. And in the past, I put some additional information here, like what the mean of the sampling distribution is, what the standard error is, all that stuff. I'm just going to roll that into the actual calculation of the confidence interval. And we've already made clear what it is we're doing, a matched pairs T interval for a population mean difference, so I don't have to write that again. You may not have seen me for all of that, but that's okay. We don't need the calculator again right now, so I'm just going to put it away because I love it when you can see my smiling face. So let's go ahead and calculate our confidence interval here. We need our formula. Before we get to that, I'm saying this is a 95% confidence interval for the population mean D. And depending on who you ask, putting the D there isn't necessary. It's a population mean, right, of this data set. But because these are matched pairs, we want to call attention to that fact and say that this is a population mean of the differences. Okay, it's the population mean of this data set, not what we started with. So it's slightly different notation. If you leave the D out, it's not that big a deal. Okay, it is a confidence interval for a population mean still, just like before. So our formula, if we're going to stay consistent with our notation for difference of a data set, okay, our confidence interval is going to be centered at the sample mean again, but it's the sample mean of the differences, x bar D. And we're going to add or subtract the critical value, which is going to be T star 9. Remember, again, degrees of freedom. We said there are 9, but that's because this sample size here is 10, minus 1 for the degrees of freedom. T star 9 times the standard error, which is going to be SD over the square root of ND. Okay. Same basic formula for the confidence interval that we used before. We're just using different notation because we've got matched pairs. So we need to know what these 4 quantities are. ND is really easy. The sample size here was 10. Now the other 3 things, we don't know them right now. We don't know what X bar D is. We don't know what SD is. And we don't know what T star 9 is. This could be a problem. Now, for the sample mean and sample standard deviation of this data set, we've already put that into L1, right? So let me bring this calculator back. I'll forget to get rid of it again, don't worry. I'll put it over here on the side. Okay, so that's our lovely histogram. If we go back to stat edit, we'll see the data set. We want the mean and standard deviation of this. We can get that by going to stat, calc at the top, and then one var stats. Okay, I believe we did this a while ago, So this isn't the first time we're doing this. We want list is L1. Freak list, I believe you can leave that blank and calculate. Yes. Okay. So we want the sample mean and sample standard deviation. X bar, it says, is 2.8. Good. And the sample standard deviation, in the output that you can see there for 1-var stats, there is Sx and sigma x. Remember, Sx is for samples, sigma x is for populations. If this were a population and we wanted the standard deviation, we would use sigma x. But we know for a fact this is a sample, so we want Sx. We're calling it Sd here. 2.53. So 1-var stats, if you put the data into your calculator, you can get the sample mean and sample standard deviation that way. It might also be the case that that information is given to you in the problem. You might not have to go through all those steps of putting the data in your calculator and getting these yourself. But now you know how to do it. The only thing left we don't know, T star 9, our critical value. I shouldn't have to tell you at this point, this is what you need to be doing. Okay, draw our curve here. We want what percent confidence? 95. That's going to leave 2.5% on either side. Now remember, this is where you can choose to either use inverse t on your calculator. You'll do 0.975 with 9 degrees of freedom. Or you can use the t-table that we showed in the last video, and you would look for 9 degrees of freedom, that row, and then your tail probability would be 2.5% or 0.025. Either way, that should give you a critical value of 2.262. All right, so we now know all 4 of these quantities. We should be able to plug them all in and get our confidence interval. I'll skip to the good part. Maybe you want to do this on your own as well. I did make one small mistake. When I said that X bar D was 2.8, I forgot the little negative sign, right? The sample mean is negative 2.8. And I should have caught that earlier because look at the data set we dealt with. Almost all of these values are negative. So the sample mean should have been negative. I fixed my mistake. I hope you saw that when you were doing it too. Okay, so our confidence interval, negative 2.8 plus or minus our critical value, 2.262, times our standard error. Standard deviation over the square root of the sample size, that's 2.53 over the square root of 10. We end up with negative 4.61 to negative 0.99. So maybe you would like to interpret this currently naked confidence interval and put it in context. What does it mean that our confidence interval is this? Give that a shot. Interpretation means everything. How do we interpret this interval? We are 95% confident that the true mean difference in resting pulse rates among men using this device over 6 weeks after MySP4 is between negative 4.61 beats per minute and negative 0.99 beats per minute. Now, most of that interpretation is just what the parameter is in context, right? Everything from here to here, everything in the brackets. The true mean difference in resting pulse rates among men using this device over 6 weeks after MySP4 is all interpreting this. That's what mu D is. This is still the same template. We are 95%, we are blank percent confident that parameter of interest in context is between blah and blah in context. That's all it is. And to be fair, you might not have had to include all that detail in what that parameter is. You might have gotten away with saying the true mean difference in resting pulse rates. there's context there. It might not be complete, but that's better than not putting it at all, right? But this is a difference in something, right? This is going back to what we originally started with. It's a difference between two data sets. So you can think of it as the difference between these two, or you can think of it as interpreting this column, which is the difference between those two, right? So this interpretation is really the one place where a matched pairs t interval is actually different than just a one sample t interval. Because an interpretation for one sample would just be, we're blank percent confident that the true mean of whatever the variable is between blah and blah. Whereas this is a true mean difference, or a difference in means. Okay. So there's just one more thing I want to ask about this confidence interval. And I also want to add quickly, this is not the only way that you had to write this. I've stated before that I like to put in directionality. So an alternative interpretation that you could have written here, I'll just read it here. We are 95% confident that the true mean resting pulse rate for men after 6 weeks of using this device is between 0.99 beats per minute and 4.61 beats per minute lower than at the start of the 6 weeks. So if you wanted to put the directionality in there and actually say something that I feel is a stronger statement, you can do that. But technically, this is this. So don't worry too much about that wording. You can keep it that way. I think this is the safer option. So other than just interpreting this interval, which we just did, there's really one other question that really gets at the heart of what is this actually saying? Why was this study done? What was the point? To see if the exercise device is effective in lowering mean pulse rates among men. So, is there evidence that the device lowers mean resting pulse rates among men during this period? This period being the 6 weeks that they use the device. Is there evidence of that? I should probably put explain after that as well. Yes or no is never a good enough answer in this class. Does this confidence interval provide that evidence? Questions like this are asking whether a certain number is in this interval or not. What's the number in question? 0. If there is evidence that it lowers the mean resting pulse rates, then 0 should not be in there. And specifically, all the numbers in the interval should be negative. Because remember, we're taking after minus before. If it reduces the rates, then the after should be lower than the before, and that difference should be negative. So, is 0 in this interval? No. Not only that, but all of the values in the interval are negative. So yes, there is evidence of this. To craft the response to this question, is there evidence of since 0 is not in the interval and all values in the interval are negative? Yes, there is evidence of I just repeated this verbatim. Okay, so if you are nervous about your interpretations or answering questions like this, don't be afraid to steal phrasing from the relevant question. Or going back to a template that we just use over and over. Okay, that should provide you some structure for how you should be crafting these responses. Right? Is there evidence of something from a confidence interval? What number are you looking for? Here it's 0. Since it's not in there and all these numbers are negative, yeah, the device lowers mean resting pulse rates. Okay. So, the main idea that I wanted you to get out of this example is that we are going to get into 2 sample t stuff. It does exist, just like it did for 2 sample z stuff for proportions. But this is not a 2 sample deal because the 2 samples were not independent. If you've got 2 samples, you need to make that determination right away. Are these samples independent or are they matched pairs? If they are matched pairs, this is the key. Take the difference in the two data sets to create a single data set. That will allow you to check conditions, go through all of your mechanics, and get your confidence interval. And if you're thinking, is that going to work the same way for hypothesis tests? Yes, it will. We will probably go through a one sample t-test and then do a matched pairs t-test. Just so you know what's coming. I want you to be shocked. This is really kind of formulaic the way we're going to go. We're going to do one sample t-test, matched pairs t-test. Then we're going to do two independent sample confidence interval and hypothesis test. And that's pretty much the end of Unit 7. That's the rest of it. So get ready. What we've already looked at here provides a great roadmap to what we're going to be doing. Nothing's going to shock you for the rest of this unit. It's all just slightly different data sets that we need to deal with. Confidence intervals, hypothesis tests. That's what we've got. Sorry for the length of the video, but I wanted to make sure that you were prepared with everything you need for your first quiz that will be coming up. There will be a progress check due as well. Make sure to check Canvas for when that is due. And we will see you in the next video. Take care.